Hmm. Maybe it's because the hover cam's running. I don't know. You can hear me okay, right? Yeah, I don't know. Well, we finished up talking about test benches last time. I'll put the chapter 4 test out later today. And that's hung up. Ah, try that again. Okay. This is chapter 5, synchronous sequential logic. And chapter objectives. You know how to distinguish a sequential circuit from a combinational circuit. Understand the functionality of SR latches, transparent latch, D flip flop, JK flip flop, and T flip flop. Know how to use a characteristic table and characteristic equation of a flip flop. Know how to derive the state equation, state table, and state diagram of a clock sequential circuit. Know the difference between Mealy and Moore finite state machines. Given the state diagram of a finite state machine, be able to write HDL model of the machine, understand the HDL models of latches and flip-flops, know how to write synthesizable HDL models of clock sequential circuits, know how to design a state machine using manual methods, and know how to eliminate the equivalent states in a state table, know how to define a one hot state assignment code, be able to design a sequential circuit with A, D flip flops, J, K flip flops, and T flip flops. And hung up again. May not be such a good day. Now, just kind of an overview of the chapter, the concepts and so forth. Handheld devices, cell phones, navigational receipts, personal computers, digital cameras, personal media player, and virtually all electronic consumer products have the ability to send, receive, store, retrieve, and process information, and represented in binary. Technology enabled and supporting these devices is critically dependent on electronic components that can store information that have memory. This chapter examines the operation and control of these devices and how their uses in circuits, and enables you to better understand what is happening in these devices when you interact with them. The digital circuits, so thus far, have been combinational. Their output depends um, only and immediately on their inputs. They have no memory. That is, they do not depend on past values of the inputs. Sequential circuits, however, act as storage elements and have memory. They can store, retain, and then retrieve information when needed at a later time. And that's the difference between what we were talking about before and what we're talking about now. Now here's a diagram of a sequential circuit. You still have the inputs, still have outputs. So inputs coming in. Now here we have a combinational circuit. Let's see. A sequential circuit is specified by a time sequence of inputs, outputs, and internal states. In contrast, the outputs of combinational logic depend on only the present value of the inputs. So this shows you the inputs coming in. is. Okay, so then you got the output coming here. It's going through some kind of memory element, and then being redirected into the combinational circuit. So you can have that loop there. Then your output's there. So our inputs here, our outputs, and then we've got our internal states that's going on. Two types of main sequential circuits, and their classification is a function of the timing of the signals. Synchronous sequential circuit is a system whose behavior can be defined from the knowledge of its signals at discrete instants of time. The behavior of asynchronous sequential circuit depends upon the input signals in any instant of time and the order in which the inputs change. Synchronous sequential circuit employs signals that affect the storage elements at only discrete instants of time. Synchronization is achieved by a timing device called a clock generator. I don't know if you remember those ones where we put the couldn't get it to work in the simulator, but we put the time delay in them, 10 ms and 20 ms and so forth. Well, this is a little bit more sophisticated in that regard. Clock is represented by identifier clock and CLK. I've got their clock sequential circuits. Where's the talk about flip-flop? There it is. The storage elements memory used in clock sequential circuits are called flip-flops. Flip-flop is a binary storage device capable of storing one bit of information. In a stable state, the output of a flip-flop is either 0 or 1. A sequential circuit may use many flip-flops to store as many bits as necessary. For example, word or data may be stored in a 64-bit value. Excuse me. So how many flip-flops would you need? Flip-flop stores one bit of information, so if you want to store one word of data, you need 64 flip-flops. You got to find that the ones we will look at be fairly straightforward, because otherwise the diagram 64 flip-flops wouldn't be possible. Now here's a synchronous clocked sequential circuit. So we have our inputs coming in. Okay, here's our memory. And we have some outputs going there. But then you also have some elements that will come on this path. Specifically one bit at a time. So that's what a flip-flop will store off. And then the block diagram here shows that it circles back around like that. So your output goes through this flip-flop and then comes back in as an input. And here's a timing diagram of clock pulses coming in here to help with the timing. Drink. I wondered that when we were talking about the combinational circuits, just combinational circuits. Because if you had inputs coming in, what happens if this one arrives first? You know, what happens if this one hasn't arrived yet? You know, you're sending voltage along. The voltage is coming in here. And at the point where this voltage has arrived, this one has not arrived, so it's got a 1 and 0, and automatically sends that out. Okay. This talks about it over here. Okay, the flip-flops, 1 or 0, sequential circuit may use many flip stars, many bits, okay. Outputs are formed by a combinational logic function of the inputs to the circuit, or the value stored in the flip-flops, or both. Because again, you have your output coming back around like that. Value that's stored in a flip-flop when the clock pulse occurs is also determined by the inputs to the circuit, or the values presently stored in the flip-flop, or both. New value is stored, the flip-flop is updated when a pulse of the clock signal occurs. Prior to the occurrence of the clock pulse, the combinational logic forming the next value of the flip-flop must have reached a stable value. Consequently, the speed at which the combinational logic circuits operate is critical. If the clock synchronizing pulses arrive at a regular interval, as shown in the timing diagram, the combinational logic must respond to a change in the state of the flip-flop in time to be updated before the next pulse arrives. Does that make sense on how that's all based upon timing? Because when you got this coming in, what happens if this is delayed? If this is not done right here, what happens if the next pulse comes in? So all important factors in this regard. The propagation delay played an important part to determine the minimal interval between clock pulses that will allow the circuit to operate correctly. Change in the state of the flip-flops is initiated only by a clock pulse transition. For example, the value of the clock is signal changes from 0 to 1. When a clock pulse is not active, the feedback loop between the value stored in flip-flop and the value formed at the input to the flip-flop is effectively broken, because the flip-flop outputs cannot change even if the outputs of the combinational circuit driving their inputs change. Thus, the transition from one state to the next occurs only at predetermined intervals dictated by the clock pulses. So when this sends that 1 through, then that triggers this to go ahead and send its value through. Five point 3, storage elements latches. Storage element in the digital circuit can maintain a binary state indefinitely as long as power is delivered to the circuit, until directed by input signal to switch states. Major differences among various types of storage elements are in the number of inputs they possess and the manner in which the inputs affect the binary state. Storage elements that operate with signal levels rather than signal transitions are referred to as latches. Those controlled by a clock transition are flip-flops. So again, if it's got a clock pulse, then that's a flip-flop. If instead it is operated with signal levels, then that's our latch. Latches are said to be level sensitivity devices. Flip-flops are edge sensitivity devices. Two types of storage elements are related because latches are the basic circuit from which all flip-flops are constructed. Although latches are useful for storing binary information for the design of asynchronous sequential circuits, they are not practical for use as storage elements in asynchronous sequential circuits. As they are building blocks of flip-flops, however, we will now consider the fundamental storage mechanism using latches before considering flip-flops. SR latch. The SR latch, they give you a picture down here. S for set, R for reset. The SR latch is a circuit with two cross-coupled NOR gates or two cross-coupled NAND gates, and two inputs labeled S for set and R for reset. You see down here are our NOR gates. Got the OR gate, and then there's an inverter on front, so that's our NOR. The latch has two useful states. When output Q is equal to 1 and Q prime is equal to 0, the latch is said to be in a set state. When Q is equal to 0 and Q prime is 1, it is in the reset state. And indicate that down here. Q is 1, Q prime is 0, then S is 1. That's our set state. Q is 0, Q prime is 1. That's our reset state. R is equal to 1. And it says if S and R are both 1s, and that's voltage, you can think of it as voltage coming in. Here's 1 at this level, 0's down here. But if they're both coming in as 1, that's forbidden. It's interesting. Let's see. Outputs Q and Q prime are normally complement each other. However, when both inputs are 1 at the same time, a condition in which both outputs are equal to 0 rather than mutually complementary occurs. Now, recognize how this works. Is we got R coming in, we got S coming in, but the output from S has to go back around and become the input for the R. The output for R has to come around and be the input for S. Let me think about this. Q is 1. Or okay, so 0, 0. Both coming in there. 1 and 1 coming in there. Let's see what it says about that. I was trying to see the difference between 0, 0 and 1, 1. Okay. However, both inputs are equal to 1 same time. Condition occurs when both are equal to 0. The device will enter an unpredictable or undefined state or metastable metastable state. Consequently, in practical applications, setting both inputs to 1 is forbidden. Under normal conditions, both inputs of the latch remain at 0 unless state has to be changed. Okay, so 0's coming in, 0's coming in. I need to set this. So if this is a 1 coming in here, if it's a 1, Q prime is 0. So that's coming through there. We got a 0 here and 0 here. And so just our set is activated. Let me draw this out. Okay, so this is a 1 coming in. This is a 0 coming in. So that's 0, that's 1. Just or would be a 1. Then our NOR would be a 0. Okay, so yeah, actually write down all of them. 1 0 0 0 1 1. One and 1. You look that up. Should give you 1, I think. Yeah, it does give you 1. Oh, I'm looking at this their diagram wrong. Because Q prime is when after it flips it. Okay, so then our NOR 0 1 0. Okay, so having the 1 come in here. Now, no matter what, if S is 1, that means our NOR is going to give us a 0. So that means a 0 is coming out of here, which explains why they have Q prime as 0 in the table. This is coming around here, so we then got a 0 coming in there. And then that would be giving us a Q of 1. Okay. Okay, so this talks about showing the function table. Under normal conditions, both inputs of the latch remain zero and the state has to be changed. The application of a momentary one, two only, the S, causes the latch to go to the set state. That's a state here. The S input must go back to zero before any other changes take place. In order to avoid occurrence of undefined next state that results from the forbidden input condition. Okay, so that's where the zero or the one and the zero comes from there. And I'm just looking at the first diagram here. Okay, so one's coming out here, that comes back into here. And if this is still a one here, then I got one and one again, which gives me a zero. That goes back in there, and assuming that's still a zero. Then 0, 0 gives me back the 1. And this is coming in down here as a 1. Okay. I see how it all flows together on that. But before they do anything else, then they have to the S input must go back to 0 before any other changes take place. If I change this to a 1, that's a 1 coming in there, which means I'd have a 0 coming out. So this would be a 0 coming out. And then that would come down here, and you'd have a 1 and a 0, which gives you a 0 coming out. So both of these then would be 0. Okay, that's what they're talking about with 2 1s coming in, giving you 2 zeros. I mean, it makes sense when you think about it. You can't be setting it and resetting at the same time. Okay. Showing the function table, a figure by 2 input conditions that must be taken by 2 input conditions cause circuit to be in a set state. Let's refresh my own memory. Set state is when we got 1 and 0. So we're talking about this first one and the second one. Those both give you a set state. Two input conditions consider the set state. The first condition, S equals 1, R equals 0, is the action that must be taken by input S to bring the circuit to the set state. Removing the active input from S leaves the circuit in the same state. Oops. 0 coming in here. Like that. S is 1. No matter what, that gives you a 0 for the NOR. 0's coming back around there. And R0, 0, 1, 0. Okay, it's going around like that. Okay, so then they say, removing the active input from S leaves the circuit in the same state. So I shut off the voltage for that. So we have a 0 coming in. So we've got a 0 there, and this is branching around as a 1. Oh, it does. Yeah, because 1, 0 from our NOR would give us 0 again, which comes around like that. Okay, so that's what we're talking about. That after you turn this on, the voltage, you change it to 0, shut off the voltage, it still maintains the same state. Okay, so after both inputs return to 0, it is then possible to shift to the reset state by momentarily applying a 1 to the R input. Okay, so we got a 0 coming in here and a 1 coming in here. And R being 1, no matter what this input is right here, gives us 0. So this is a 0 coming out. And that's a 0 coming back around there. So 0 for both the inputs. 0, 0 would give us a 1 coming out. So that'd be a 1. And that's coming back around as a 1 there. And both of them being 1s again gives us 0. So then it just completes the cycle. So I'm saying that should be 0, 1. Let's see if that's true. 0, 1. It says the 1 can then be removed from R, whereupon the circuit remains in reset state. Thus, with both inputs S and R equals 0, latch can be either in the set or the reset state, depending upon which input was most recently a 1. Oh, this is a NAND gate showing the same thing. Okay, so we got our S and our R. Q. These are branching back through. Like that. Okay, so if these are both 0 initially, okay, so I got 1, 0, 1, 1, 0, 1. I got 1, 1 here again, but 0, 0. Just the AND. That'd be 0. This would be a 1, 0, 1, 0. Then the NAND flips that, inverts it. 1 0 1 0 1. So 0 0. If S is 0, no matter what, if S is 0, then the NAND gate's giving us a 1. So that means I have 1 coming out here. That's coming back around. And 1 and 0 is 0, and then that gives me a 1. And that's coming back around. Okay, so it continues that same process. So Q and Q prime should both be 1s. Oh, that's our forbidden state. 0 0 is forbidden. Then I talk about the SR latch with 2 cross-coupled NAND gates, is shown in this figure. It operates with both inputs normally at 1, because a 0 0 would give you that forbidden state. Okay, so I have 1 and 1 coming in. And the application of 0 to the S input causes output Q to go to 1. So if I change this to 0, this would give us a 1, because 0 times anything is 0, and then you invert it, and that gives you a 1. And then that's coming back down here. So we got 1 and 1, which is 1. That gives you a 0 coming out here. So it causes output Q to go to 1, putting the latch in a set state. When the S input goes back to 1, so you change that back to 1. The 0 is coming up here. Okay, the circuit remains in the set state. Because when that 0 comes back up here, 1 times 0 is 0, and then you invert it, gives you a 1, so it doesn't change. And that 1's still coming down here, and 1 and 1's 1, and then you invert it, and it gives you 0. Okay, so that's what they mean. After both inputs go back to 1, we're allowed to change the state of the latch by placing a 0 in the R input. So to get this to change state, we change this to a 0. 0 times anything is 0, then you invert it, and that goes to a 1. And this comes back here. 1 and 1's 1, then you invert it, and that goes to 0. This action causes the circuit to go to the reset state. So this being 0 and this being 1 is a reset state. And stay there even after both inputs return to 1. So if I change this back to 1, so that's coming in as a 1. This is coming to 0. 0 times 1 is 0. Invert it, stays a 1. Then that 1's coming here. 1 and 1's 1. Invert it, and it goes to 0. So it doesn't change. Conditions forbidden for the NAND gate is both the inputs being equal to 0 at the same time. An input combination that should be avoided. Of course, what goes through my mind when I read that is what happens when you do have that forbidden state. Does your circuit fry, or it just doesn't work, or what? Does that make sense how the NAND works in these in the NOR? In comparing the NAND with the NOR gate, Note that the input signals for the NAND require the complement of those values used for the NOR latch. Because the NAND gate requires a 0 signal to change the state, is sometimes referred to as S prime R prime latch. The primes, or sometimes bars of the letters, designate the fact that the inputs must be in their complement form to activate the circuits. Operation of the basic SR latch can be modified by providing an additional input signal that controls when the state of the latch can be changed by determining whether S and R or S prime and R prime can affect the circuit. An SR latch with a control input is shown in figure 5.5. So here's our enable. Consists of the basic SR latch, so all that's the same, and two additional NAND gates. So we got our two additional NAND gates here. The control input E sub EN acts as an enable signal for the other two inputs. The outputs of the two additional NAND gates stay at the logic 1 level as long as the enable signal remains a 0. If you change that to 1, so you have voltage coming in there. If S is 1 and this is 0, 1 and 1 is 1 inverted 0, so that's 0 coming in. And then if I have this is 0 and this is 1, 1 and 0 is 0, inverted to 1, so that's a 1 coming down there. This would give me a 1. So this is 0, 0 times anything 0, invert it and gives me 1. That's a 1 coming down here. One and 1's 1. Inverted goes to 0, so that's 1, 0. Okay. That's where I left off. To change the reset stage, the inputs must be S is 0, R is equal to 1, and enable is equal to 1. The set state, I guess this has to be a 1, this has to be a 0 for overdrive. Okay, in either case, when EN returns to 0, the circuit remains in its current state. Okay, so if I had a 1 coming in here, this is a 1, 1 and 1 is 1, inverted, that's a 0. So that's a 0 coming in there. I'll change this to a 0. 1 and 0, 0, inverted, that's a 1. But then this is coming through. 1 times 0, 0, inverted to 1. So that's, okay, I see what you're saying then. Let's see. So the state of the output does not change regardless of values of S and R. Moreover, when EN is equal to 1, both the S and R are equal to 0. The state of the circuit does not change. These conditions listed in the function table. Find the diagram. Okay, indeterminate condition occurs when all three inputs are equal to 1. This condition places zeros on both inputs of the basic SR latch, which puts it in the undefined state. When the enable input goes back to 0, one cannot conclusively determine the next state because it depends on whether the S and R input goes to 0 first. The indeterminate condition makes this circuit difficult to manage and is seldom used in practice. Nevertheless, the SR latch is an important circuit because other useful latches and flip-flops are constructed from it. The question becomes, and that's why I've been trying to emphasize this with the tables, is you got this output coming in as this input, and you got this output coming in as this input. And the question would be, well, which one has to go first? And that's why I've been tracing those to indicate that it doesn't matter. When this is coming in as a 1 in our tables, for example. No, that might have been a bad one to choose. But like when S is coming in as a 0. Here's S0, here's S0. Then the result is a 1. It doesn't matter what R is. Along the same lines, if R is equal to 0, then the NAND produces a 1. It does not matter what S is. But to indicate that down here, if all three inputs are equal to 1, then it depends on which one gets processed first in terms of what your result is. So it's unpredictable. Does that make sense on these lines right here? Understanding that it doesn't matter for the normal conditions which one goes first? The D latch. One way to eliminate the undesirable condition of the indeterminate state in the SR latch is to ensure that inputs S and R are never equal to 1 at the same time. This is done in the D latch. This latch only has two inputs, D and an enable. The D input goes directly to the S input, and its complement is applied to the R input. As long as the enable input is 0, the cross-coupled SR latch has both inputs at 1 level, and circuit cannot change state regardless of the value of D. The D input is sampled when our enable is equal to 1. If D is equal to 1, the Q output goes to 1, placed in the circuit in the set state. If D is equal to 0, output Q goes to 0, placed in the circuit in the reset state. Okay. So if D is equal to 1, coming in here, coming down here, let me think this through. Enable 0. That's a 0 coming in there. 0 times anything 0, that gives me a 1. So that's 1 coming in there. I'm going to draw this. I'm not going to be able to see it otherwise. Okay. Um, as long as the enable input is 0. Cross-coupled SR latch has both inputs at one level, and circuit cannot change state regardless of the value of D. Okay, so I have 0 coming in here. 0 times anything is 0. Inverted becomes a 1. Down here, I have 0 coming in here. 0 times anything is 0. Inverted becomes a 1. Let me think. This was 0 to begin with, because there's no voltage going through, like the first time. Then 1 times 0, 0, inverted becomes a 1. That comes back around there. 1 times 1 is 1. That gives me a 0. So these are both 1s, I believe. Okay, and just maintains that state. Okay, so then if I change this to a 1, according to the table, it's a 1 coming in there. We got 1 and 1, which is 1. Inverted becomes a 0. Down here, that's going to become a 0. Zero times anything is 0. Inverted becomes a 1. Okay, this doesn't say anything about Q prime. This is just saying about Q. Okay, so that makes sense. Because 0 times anything is 0, and then that goes to 1. Okay, I see what you're talking about. So Q is equal to 1 is our set state. Now, if my D was 0, this is coming in here. 0 times anything is 0. Invert it becomes a 1. Like that. This is coming down here, and it's and go through this inverter, so it becomes a 1. My enable is still 1, so that's a 1. 1 and 1 is 1. Inverted becomes a 0. 0 times anything is a 0. Inverted becomes a 1. That's a 1 coming out here, coming through here. And 1 and 1 is 1. Inverted becomes a 0. Q is equal to 0 is the reset state. Okay, I see how that works. D-latch receives that designation from its ability to hold data in its internal storage. It's suited for use as a temporary storage for binary information between a unit and its environment. The binary information present at the data input of the D-latch is transferred to the Q output when the enable input is asserted. So we got our data coming in here, and so when enable it, with E is equal to 1, then that passes your data on through to the Q. So it's holding that memory storage. D is equal to 0 coming through here. Sorry, D is equal to 0 coming through here. enables 1. That causes 0 to go through. Okay, so that's just how you release the data from the storage there. Output follows changes in data input as long as the enable input is asserted. The situation provides a path from input D to the output, and for this reason, the circuit is sometimes called a transparent latch, because it's just allowing the value of D to go over to Q. When the enable input signal is deasserted, the binary information that was present at the data input at the time of the transition of enable occurred is retained, stored. So it's stored in here. And then once I enable it, then that releases it. Note an inverter could be enabled or placed at the enable input. Then, depending upon the physical circuit, then the external enabling signal will be value of 0, active low, or 1, active high. Now, instead of writing that on every diagram from now on, this is how they'll represent it. Latch is designated by a rectangular block with inputs on the left and outputs on the right. So you got your S and R, and then your outputs coming in over here. The graphic symbol for the SR latch has inputs S and R indicated inside the block. In case of a NAND gate latch, bubbles are added to the inputs to indicate that setting and resetting occurs with a logical 0 diagram, which is this right here. The graphic symbol for the D latch has inputs D and EN indicated inside the block. Of course, got our outputs there. Let me grab a drink here. It's amazing to me that people were able to come up with this, and this is how all of our electronics works. I shouldn't say all, but this is kind of a basic foundation of our electronics. Okay, flip-flops. Changing the control input of a latch or flip-flops switches its state. The momentary change is called a trigger, and the transition is causes to trigger the flip-flop. The D latch with pulses in its control input is essentially a flip-flop that is triggered every time the pulse goes to logic 1 level. As long as the pulse input remains at this level, any changes in data input will change the output and the state of the latch. As seen from the block diagram of figure 5.2, which is over here, a sequential circuit has a feedback path from the outputs of flip-flops to the input of the combinational circuit. So it has your output coming back here and is your input. Consequently, the input of the flip-flops are derived in part from the outputs of the same and other flip-flops. When latches are used for the storage elements, a serious difficulty arises. The state transition of the latches start as soon as the clock pulse changes to the logic 1 level. The new state of the latch appears at the output while the pulse is still active. This output is connected to the inputs of the latches through the combinational circuit. If the inputs applied to the latches change, While a clock pulse is still at logic 1, latches will respond to new values and new output state may occur. The result is an unpredictable situation since the state of the latches may keep changing for as long as the clock pulse stays at the active level. Because of this unreliable operation, the output of a latch cannot be applied directly or through combinational logic to the input of the same or another latch when all latches are triggered by a common clock source. Flip-flop circuits are constructed in such a way to make them operate smoothly when they are part of a sequential circuit that employs a common clock. The problem with the latch is that it responds to a change in the level of the clock pulse. It says, shown in figure 5.8a, a positive level response in enable input allows changes in the output when D input changes, while clock pulse is at logic 1. Positive level response. Enable input allows changes in output. Okay, it doesn't show the enable. He was talking about it. Positive transition is defined as a positive edge, and negative transitions as a negative edge. There are two ways that a latch can be modified to form a flip-flop. One way is to employ two latches in a special configuration that isolates the output of the flip-flop and prevents it from being affected. While the input to the flip-flop is changing. Another way to produce a flip-flop that triggers only during signal transition from 1 to 0 or 0 to 1 or 1 to 0 of the synchronizing signal clock. The important part there is when it's going from 0 to 1, that's referred to as a positive edge response. So it's going up. If it's going from 1 to 0, that's called a negative edge response. It's going down. You get a voltage up here, full is at 1. Okay, construction of a D flip-flop with two D latches and inverter shown in figure 5.9 is often referred to as a master-slave flip-flop. First latch is called the master, and the second one is called the slave. The circuit samples a D input and changes its output Q only at the negative edge of the synchronizing or controlling clock. When clock is 0, the output of the inverter is 1. Okay, so 0 is coming in here. Okay. Okay, I see. Yeah, because when it's a 0, your enable's 0. So that means that the Y is what's coming through here. That's what you're saying. Um, when the slave latch is enabled and its output Q is equal to the master output Y. Because the coming in as 0 here goes to this inverter into 1, so that's enabled. So that means whatever the value is here is just going through. Um, when the input clock changes to the logic 1 level, the 1 comes in here means this is enabled. That means a D is passing in and being stored in this memory location. But the slave is disabled because there's the 1 coming in inverts, becomes a 0 and comes over here, so sets this down. Slave, however, is disabled as long as the clock remains at the 1 level because its enable input is equal to 0. That's what we're just talking about. Any change in the input changes the master output at Y, but cannot affect the slave output. So it changes this Y, but won't affect this. When a clock pulse returns to 0, so this changes to 0, master is disabled because the 0 is coming up here for enable, so this is disabled. This is a 1, so it's coming through here and is isolated from the D input. At the same time, the slave is enabled, so this is now enabled, and the value of Y, which is right here, is transferred straight on over to Q. Thus, a change in the output of the flip-flop can be triggered only by and during the transition of the clock from 1 to 0. The behavior of the master-slave flip-flop just described dictates that the output may change only once. Changes in the output is triggered by the negative edge of the clock, and the change may occur only during the clock's negative level. The value that is produced at the output of the flip-flop is the value that was stored in the master stage immediately before the negative edge occurred. It's also possible to design a circuit so that a flip-flop output changes on the positive edge of the clock. This happens in a flip-flop that has an additional inverter before the clock terminal and the junction between the other inverter and input EN of the master latch. Such a flip-flop is triggered with a negative pulse, so the negative edge of the clock affects the master, and the positive edge affects the slave and the output terminal. Drink. I had to get some caffeine before class. Bless those people out there creating my new Xbox and PlayStation and phone and TV. Because this stuff is dry as can be. I don't know how anybody can get excited about this. No, I'm sure if you do have trouble sleeping, you just watch this video over and you have no trouble. No offense to somebody who gets excited about this stuff. I find it interesting, but it's just doesn't really trip my trigger. But then again, everybody has their own areas where some people find programming itself boring as can be, and I find it exciting. Okay, let's see. Here's It's there, it's kind of buried, but they say it uses 3 SR latches. So remember our SR latch? Had 2 NAND gates. So here's 2 of them. Here's 2 of them. Wait a minute, let me think. No, I bet this is what we're talking about. So 2 NAND gates here, 2, and then 2. Okay. Uses 3 SR latches as shown. The two latches respond to the external D data. Oh, I see. Because D's coming in here, then it's coming out here and circling back around. It's input into that, which then its output is then input into this. And it also goes here and circles back to that. And clock inputs. Okay, clock obviously there and there. And I guess indirectly by coming back around there and back around here. So it controls really all of those. The S and R inputs in the output latch are maintained at logic 1 level when clock is equal to 0. This causes the output to remain in its present state. Input D may be equal to 0 or 1. Let me draw that. Okay. Clock is 0. So we have 0 coming in here. Input is 1. 0 is coming in here. 0 times anything 0 inverted is 1. So that's 1. Same thing here. This is coming as a 1. So that's branching back here. That's a 1 there. 1 and 1 is 1. Inverted becomes a 0. So 0 is coming out here. It's coming in here. 0 times anything is 0, and inverted it's a 1. So that's still a 1. It's coming around here to 0. 0 times anything is 0. Inverted becomes a 1. That's coming down here. 0 and 1 is 0. Inverted is 1. Okay. So then S is 1. R is 1. If these were if these were ones before, or one here and one here, let's say. See, 1 coming around there. 1 and 1 is 0, so 0. 0 times anything's a 1, so I didn't change the state. I guess it can't be 1 and 1. This is 0. 0's coming back over there. That becomes a 1. 1, 1, 1, 0. Okay, I see how it doesn't change state. When clock becomes 1, so that's a 1. This is a 1 coming in. 1 and 1 is 1. Inverted becomes a 0. Okay, here's a condition I'm looking for. Similar, if D is equal to 1, when clock goes from 0 to 1, which is what I just said, S changes to 0. So that makes sense, because we have a 0 coming out here. What happens down here? Or it doesn't matter. Okay, 1 going in there, 1 going in here. I guess this was 1 before. This was 0 before. So that goes to 1. I guess all that matters is they're looking at Q. Never mind. So Q is 0. Of course, the question comes to mind, why aren't they looking at Q prime? They do have Q prime on there, but they don't focus on that at all. Okay. So it's on page 256. It says, in sum, when the input clock and the positive edge triggered flip-flop makes a positive transition, the value of D is transferred to Q. A negative transition of the clock, i.e. from 1 to 0, does not affect the output, nor is the output affected by changes in D when the clock is in the steady logic 1 level or the logic 0 level. Hence, this type of flip-flop responds to the transition from 0 to 1 and nothing else. Timing of the response of a flip-flop. The input data and the clock must be taken into consideration when one is using edge-triggered flip-flops. There's a minimum time called the setup time, during which a D input must be maintained at a constant value prior to the occurrence of the clock transition. Similarly, there's a minimum time called the hold time, during which D input must not change after the application of the positive transition of the clock. Propagation delay time of the flip-flop is defined as the interval between the trigger edge and the stabilization of the output to new state. These and other parameters are specified in manufacturer's data books for specific logic families. Graphic symbols for the edge triggered D flop are shown in figure 5.11 up here. So they won't draw this each time they refer to the D edge, positive edge. They'll refer to these up here. It's like difference between those is the negative edge has a bubble in front. Other than that, they look the same. Okay, dynamic indicator greater than denotes the fact that the flip-flop responds to the edge transition of the clock. Bubble outside the block, adjacent to the dynamic indicator, designates a negative edge for triggering the circuit. The absence of a bubble designates a positive edge. We'll get to the characteristic equation, so let's talk about this last piece. Very large integrated circuits contain several thousands of gates within one package. Circuits are constructed by interconnecting the various gates to provide a digital system. Each flip-flop is constructed from an interconnection of gates. The most economic and efficient flip-flop constructed in this manner is the edge-triggered D flip-flop. This requires the smallest number of gates. Other type of flip-flops can be constructed by using the D flip-flop and external logic. Two flip-flops less widely used in the design of digital systems are the J, K, and T flip-flops. There are three operations that can be performed with a flip-flop: set it to 1, reset it to 0, or complement its output. With only a single input, the D flip-flop can set or reset the output depending on the value of the D input immediately before the clock transition. Synchronized by a clock signal, the JK flip-flop has two inputs and performs all three operations. The output diagram of a JK flip-flop constructed with a D flip-flop and gates is shown in figure 5.12. The J input sets the flip-flop to 1, the K input resets it to 0, and when both inputs are enabled, the output is complemented. This can be verified by investigating the circuit applied to the D input. D is equal to J Q prime plus K prime Q. J is equal to 1, then K is equal to 0. And that flips it, and that's a 1, and that's a 1. And here's Q prime. So if that's a 1, that's Q prime, then this would give you whatever Q prime is coming out. This would give you whatever Q is. Because 1 and Q is equal to Q. And they tell you that. J and Q prime. J and Q prime. That corresponds directly to what they're talking about there. And then K prime and Q. Well, K prime comes from the inverter here, and Q comes from this over here. So K prime and Q is that part. And then the plus in between them is our OR right here. And that's how what dictates what D is. So knowing that, you can, if J is 1 and K is 0, so I got 1 here, 1 and 1's 1. There's a plus, and K prime is 1, Q is, okay, I'm messing up. Okay, that's 1 and Q prime, so that's Q prime. This is 1, so that's 1 and Q prime, or Q. So that's Q prime and or Q, which is always equal to 1. That's true. Because 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 1 is 1 in terms of this. So next clock edge sets the output to 1. When J is 0, that drops away. K is 1, so that drops away. So D is equal to 0. So next clock edge resets the output to 0. When J is equal to K is equal to 1, that's 1, and this would be 0. That drop away. So I'd have Q prime. Next edge complements the output. When both J equals K equals 0, J equals 0, that drops away. K is 0, that becomes K prime is 1, so that becomes Q. The clock edge leaves the output unchanged. It's similar to graphic symbol with D flip flop, except now we put some mark J and K. It's just talking about the graphic symbol down here. We got J and K. The T toggle flip flop is a complementing flip flop. That's over here. Can be obtained from a JK flip flop, which inputs J and K when inputs J and K are tied together. So T is tying these two together. When T is equal to 0, so T is 0, then J and K are both 0. Of course, then J and K being 0 helps you figure out what this is. Clock edge does not change output. When T is equal to 1, J is equal to 1, K is equal to 1. So this would drop away, and I give you this. Complements the output. Complementing flip-flop is useful for designing binary counters. T flip-flop can be constructed with a D flip-flop and the exclusive OR gate as shown in figure 5.13. Expression for the input is given by this. T Q prime plus T prime Q. And that takes us to characteristic tables. I don't think I'm going to do that today. Tackle that on Monday. And I'll put the test out there for chapter 4. Questions or anything? Okay, let me go ahead and stop the recording.